Um, I would like to thank Professor Stonefels for the invitation. It's always a great pleasure to be here at KAIST, where I spent the best years of my life so far. So my title was initially Geometry, Algebra, and Computation, which was a little bit too ambitious. So I put in this in-moduli theory later on. And at least I gave this talk twice in Korea, and at least the geometry part. So if you have heard this before, then I must apologize in advance. So since there are non-algebraic geometers, so let me spend 3 minutes talking about objects in algebraic geometry. So does this work? So here, so F1 algebraic varieties, it's just the common zeros of some polynomials. So example is the elliptic curve. So if you take the cubic equation, then we usually use this notation V of these polynomials. So V of f and z minus 1 union V of these two polynomials. Then, and the picture is, let me think about this. Since this is the curve C at the bottom, here is Z, so it's on Z equals 0, and y squared minus x cubed, then that's the cuspidor curve. And if you normalize it, then you're going to get this smooth blue curve, and this curve is another elliptic curve. And the particular shape is not important at all. I'm just showing you an example. And there are also projective varieties. And you take the projective space and you take polynomials, but in this case you should take the polynomials to be homogeneous. An example is you take a point, and we call this blow up of projective plane at this point, and it's given by this single polynomial equation, homogeneous of degree 2. So I copied this curve off the website, Donald Arapra's website. And if you see this curve, I wish that it didn't spin around. But if you look at this picture closely, then you see this cuspidor curve and on the yellow plane. And if you use this blow up, then you can desingularize this cusp, and that's the red curve. And, so my main interest is moduli theory. So a moduli space is, as I said, it's just the isomorphism classes of objects that you're interested in. And it's got certain universal properties, which I'm not going to use too much in this talk. So the term moduli was first used by Riemann, who lived for only 40 years. So I'm 40 years now. So what he proved is you use G+1 Riemann spheres, and you can slit and sew to get a genus G Riemann surface. And Riemann proved that by using some covering argument. He showed that that process depends on 3G minus 3 modulus. So he was the first one to use this term modulus. And after that, we are a lot of us are use this moduli everywhere. And although this has got nothing to do with algebraic geometry, I want to start by talking about plane isometries. So isometry is a map which preserves distance. So So, and we learned from, it's not high school, it's undergrad course in geometry, that plane isometry is a composition of orthogonal transformation and translation. So if you use complex coordinate, you can write it as AZ plus B. So adding B is the translation parts, and this A times Z is the orthogonal transformation. And this is a rotation unless A is 1. And you can easily compute the center of the rotation just by equating AZ plus B equals Z, and solve for Z, then you get this center. And it's rotation by the argument of the complex number A. And if you use Z bar, the complex conjugate, then Z bar is the reflection about the x-axis. So therefore, you're going to get what's called glide. So glide is, you take a gliding axis, and that's going to be a reflecting line. And you take a translating vector parallel to the reflecting line. And what you do is, you first reflect and then use the translating vector to move your points around. So any plane isometry is determined by 3 points. So you take the 3 points PQR, and what glide does to PQR is you move that triangle to that triangle, and that's what the glide does. So this is plane isometry. So where is moduli? If you think about moduli, then it is completely determined by A and B, and you can think of the following space. So moduli of plane isometries is its orthogonal transformation, which is parameterized by O of 2, O2, I should say, not O, and translating vector is in the plane, so it's R2. So that is topologically S1 cross R2 disjoint union with S1 cross R2. O2 has 2 components, 2 SO2s. So S1 cross R2, then you've got, it's a torus, open torus. So you have disjoint union of 2 tori. And if you think about it, this part is the translation. When A is equal to 1, and that's the translation. And when A is not 1, then it's rotation. And when B plus AB bar is not equal to 0, then it's going to be a glide. And when this holds, it's going to be a reflection. So by thinking about this moduli space, then you have a good understanding of the distribution of the geography of the plane isometries. So that's what's good about thinking about moduli space of the objects that you are interested in. Okay, now to algebraic geometry. And this picture is from the book by Rees on Notes on Geometry. So plane cubics, elliptic curves. So plane cubics, it's a zero locus of cubic equation, which is completely determined by those 10 coefficients. For instance, you take that cubic equation, and you can write it as in a very complicated manner as that. Then that corresponds to the vector -1, 0, 1, 0, 0, 0, 0, 1, 0, 0. Now you want to identify 2 plane cubics if you can get one from the other by linear coordinate change. So you take plane cubics and you mod up by coordinate change. That's like quotienting P9 by SL3 action. And in this case, coordinate change really is equivalent to, it equals isomorphism. So any isomorphism between two plane cubics is going to come from linear coordinate change. It's a non-trivial fact. So in this case, moduli space of plane cubics will be, well, in general, like this. So in this case, moduli of plane cubics is these plane cubic sets and isomorphism. So in general, moduli space is more often than not, you have some parameter space and you've got some group action identifying these isomorphic objects. So if you construct this quotient space, then you're going to get the moduli space that you want. But the problem is construction of quotient space in algebraic geometry is not automatic. As you can see from the following example. So here, bad degeneration of elliptic curves. So I'm going to take that cubic equation. It depends on one parameter called t. And if you let t go to 0, then what you're going to get is y squared equals x cubed. And you've seen the picture of that curve. It's the cuspidal curve. Okay. Now, I'm going to start from this cubic equation, this elliptic curve, and make a coordinate change. So when t is not 0, I can make this coordinate change by letting x prime equal to t squared x, y prime equal to t cubed y. So t is not 0 here. If you make this coordinate change, then you safely divide the whole equation by some power of t, then what you're going to get is this equation. Okay. So since you obtained c prime t from ct by a linear coordinate change, these two curves are isomorphic. They are in the moduli space. They are the same curve, same point. Now, but in this case, if you let t go to 0, then what you're going to get is y squared equals x squared times x minus z. So that is a nodal curve. So this is a problem because these two are isomorphic when t is not 0. But the limits are not isomorphic. So you've got, if you think about moduli space parameterizing these plane cubics, then you have the same points depending on a parameter t, but you've got two possible limits. So you have to choose one of them. So this is what I've been saying. Ct and c prime t are the same points in the moduli space, but the limits are not the same. So if you want to have a unique limit property, then we need to keep one and discard the other. So the problem is, what is the correct curve to pick? So we need a reliable system to pick the correct limits, whatever correct means. So that's provided by Mumford's GIT. So to understand a quotient space, what do? If you do not understand the space, then we try to understand the functions on the space. So what are the functions on the quotient space? If you think about it, so this is the quotient that we want to construct. And a function on that quotient space, if you pull back to the space x that you started with, then it's going to be constant on the g orbits, right? Because any points on the orbit, same orbit, are going to get identified in the quotient space. The function is constant on the orbits. So what you realize is regular functions on the quotient space is G invariant functions on the space that you started with. So that's why this ring of invariance plays an important role in algebraic geometry. So ring of regular functions is subring of G invariant regular functions on X. So C bracket X is the ring of regular function. I'm not defining what regular means, but you can think of it as close to locally polynomial functions. So theorem of Hilbert-Weih-Habush is if G satisfies this property called the reductivity, then the ring of invariance is finitely generated. This is in any characteristic. So now, since it's finitely generated, you can pick. So I'm going to look at my ring of invariance. This is going to be the ring of functions of my quotient space. And I'm going to take generators, finitely many generators of this ring of invariance. Then what you do is the quotient space is going to be image of this map. So this is very loosely formulated words, but it's basically true. If you choose the ring of invariance, the generators of the ring of invariance, then the quotient space is going to be image. Then, but what's important is that if these invariant functions all vanish at some point x, then these coordinates are all 0, and it's not a point of the projective space. So the map phi is not going to be defined at x. So that's the problem. Oh, I wish one of them kept the previous slide. So let's go back to the moduli of elliptic curves. So we had this SL3 action on the ring of these coefficients. And it has been shown a long time ago, some 6 years ago, that it's generated by two invariants we call S and T. That's a totally non-trivial fact. And one of them is of degree 4, the other is of degree 6. Oh, not more than 50. It's in 1850, so very long time ago. And this J invariant is 16, this fractional polynomial, rational polynomial. And what's important is, look, these are the generators of the ring of invariance, and they precisely vanish at this curve, y squared z minus x cubed. So if you remember, we had two possible limits, and one of them is not going to be defined by these regular functions on the quotient space. Right? So this is not defined in P1 with homogeneous coordinates s and t, because the all invariant functions vanish on that curve. So as you can see, this was done in 1850, where a computer was not really available. And if you want to see, S and T are given like this. And I find it amazing that someone could compute that by hand. I could not have done it. Maybe Bernd could have done it. And if you remember y squared z minus x cubed, then there are only two non-zero coefficients, right? And if you plug it in there, then you can see easily that s and t both vanish. So what does it tell you? Look, this is the original problem. We had two possible limits. And what GIT tells us is that if you look at the ring of invariant functions, then this is not really defined. Therefore, and you can compute S for this curve, and it's -1/81. So what GIT tells us is that this curve is bad, and this is the correct limit. If you want to form the quotient space by using algebraic geometry. Okay. I think I'm going too fast. Do you have any questions?
So the value of S and T for the original form, C and T, is the same on the generation?
Sorry, I did not catch your. What are the same on the degeneration?
The form you started with is T. The values of capital S and capital T for that curve.
Right.
Constant in degeneration, or what happens to that?
They are constant when T is not 0. But when T is 0, then it's not really a G orbit, right? It's in the closer of the G orbit. So you could get something different. So it's constant on these, but as T goes to 0 here, it's to 0, but it's not 0 there. Right? Okay, so construction of quotients. So let X be a projective variety, and an algebraic group is acting on the projective variety X, and SS denotes the open set of semi-stable points at which an invariant function does not vanish. So semi-stable points, a point is called semi-stable if there is an invariant function that does not vanish at the point. Okay. It could be empty. And Mumford's theorem is that there exists a projective quotient, which we call XSS. Usually we use 2 slashes, but here I'm using just 1. And there's a map from the semi-stable point locus to this projective quotient. And if you look at it locally, so these are projective varieties. Oh, this is projective and this is only quasi-projective. And if you take an affine open from the semi-stable locus, then locally the quotient is going to be defined by the ring of invariance. Okay. So it's not just a quotient in the set theoretic sense, but if you look at the ring of regular functions, then the quotient space has ring of regular functions exactly the ring of invariant functions. Okay, so plane cubics. This is a slide we have seen before. So I've got these coordinates. Wait a second, what am I doing here? I guess I did not need. Now before, in the plane cubic case, we needed only one equation. So what we needed to do is just take the coefficients of the single equation, right? But if usually you're going to need many equations to define a curve in a higher dimensional projective space. So what do we do? Suppose that a curve C is defined by these S equations inside the projective space. Then what I'm going to do is I'm going to again look at the coefficients of those defining equations, these AI alphas. And I'm going to assume that degree of these defining equations are all the same, so that they're essentially using the same monomials. Not essentially, they are using the same monomials. And what I'm going to do is I'm going to start with the curve C, look at these defining equations, and look at the coefficients of the defining equations, and form the following. The first equation, I'm going to get a vector, coefficient vector. And second equation, I'm going to get another coefficient vector, and so on. So I'm going to get S many coefficient vectors. So before, the elliptic curve was in the plane was defined by a single equation. So I only needed one row vector, right? That corresponded to points in P9. So here, what I need is, I start with a curve, and I'm going to get S many row vectors. And this is a point in the Grassmannian of S planes in this degree m piece of the polynomial ring. So before, in the plane cubic case, our parameter space was P9. Here the parameter space is the Grassmannian. Okay, now I'm going to use some sort of canonical embedding. Let me go back. Here the problem is, if I just use any kind of embedding, then I have no control over the number of equations that I need. So what I do is, so I want to use the same S for all the curves that I'm interested in. So that I use one parameter space, right? So if I just use different embeddings for every for different curves, then I'm not going to get a single parameter space. So to have a control over this number S, what I'm going to do is I'm going to use some sort of a canonical method for embedding these curves in a projective space. So if I use, then that's going to ensure that the uniform number S and degree m of defining equations are used. So if I have a non-singular projective curve of genus G, then I take the sheaf of homomorphic one forms, and I use what's called the new canonical embedding of C. And if I use this embedding for every smooth projective curve of genus G, then it's going to be cut out by the same number of equations in same degree, so that I can use a single Grassmannian to parameterize all these curves. So that does not depend on the curve C. So this is the important part. So Hilbert points is, if I use this canonical, pluricanonical embedding, then I get this matrix, which you can think of it as a point in the Grassmannian. And I'm going to call this point in the Grassmannian the empty Hilbert point of C. And this guy, H nu m, is the set of all these points I choose where C runs through all non-singular genus G curve. And this is called the Hilbert scheme of smooth projective curves of genus G. And obviously, you have this linear coordinate change, right? You have a single C in P. This n is the dimension of that space, right? This space. You have coordinate change, right? You can C is embedded in this projective space. Then you have coordinate change, and it's going to act on the Hilbert scheme. So as before, we had plane in the plane cubics. This H nu m is just going to be P9, okay? And SL3 was acting on P9, you take the quotient and you get the moduli of plane cubics. In this case, you're looking at this Hilbert scheme, and you mod up by the linear coordinate change, then you're going to get the moduli space of genus G curves. So this is what I said just now. And what's important in this picture is that it depends on two parameters, two choices. So nu and m. What was nu? Nu is the embedding choice of the curve in the projective space. And m was the degree of the equations. So if you look at it, the resulting moduli space depends on the choice of the embedding of the curve and choice of the degree of the equation. And also the semi-stability. So if you choose different nu and different m, you're going to get a different ring of regular functions. You're going to get different invariant functions. So the semi-stability also depends on the choice of nu and m. So that the resulting moduli space depends on nu and m. So the problem that I have been working hard for the last decade or so with Brendan Hesed and Professor Yongnam Lee here at KAIST is this problem. Describe the moduli spaces associated to various nu and m. So if you choose different embedding of curve, and if you choose different equations, what is the resulting moduli space? And now let me quickly define the stability condition. So Deligne-Mumford stable, you probably have seen this before. A curve is Deligne-Mumford stable if it has only nodes as singularity. Node is just x, y equals 0. And finitely many automorphisms, finite automorphism group. So the same condition is that if you have a smooth rational component, it has to meet at least 3 points. If you fix 3 points on P1, then there is no automorphism, right? So this is a picture of node. So a classic result of Deligne and Mumford is if you choose nu bigger than or equal to 5 and choose m huge, very, very large, larger than what's called the Gatzman number, then the resulting moduli space is the moduli of Deligne-Mumford stable curve. So now at this point, for the later half of the talk, I want to emphasize that if a curve has got bad singularity, then it affects the stability. Curve cannot be too singular to be semi-stable. This is an important point. So for instance, in this nu bigger than or equal to 5 and m huge case, this ordinary cusp is even too bad to be semi-stable. And this is a curve with too many automorphisms. There are lots of automorphisms of P1 that fix 2 points, right? So infinitely many automorphisms fixing 0 and infinity. And I'm going to introduce just one more stability condition. In our work, we introduced at least 3 other kinds of semi-stability, but this is going to be the end for the stability conditions. So pseudo-stable this is due to David Schubert, a student of David Giesecke, in the 80s. It allows nodes and cusps. So before, in the Dillon-Mumford stable case, only nodal singularity was allowed. Now a cuspidal singularity is also allowed, but it does not allow no elliptic tail, which means elliptic tail is, as the term suggests, it's a genus G curve, and it's got an elliptic component, genus 1 subcurve, meeting the rest of the curve in one point. So this is not allowed. So this is a new condition. This is a perfectly fine Dillon-Mumford stable curve, but it's not pseudo-stable. And how does it come about in the moduli space construction? When you take nu equals to 4, and when you take m huge, so before Dillon-Mumford stable was you take nu bigger than or equal to 5, right? But if you take nu equal to 4, this is a different choice of embedding of curve in the projective space. Then what you get is that the resulting moduli space parameterizes exactly these curves. Not these curves, the pseudo-stable curves. So again, the important thing that you need to take away from these slides is that you do GIT to construct moduli space, and the semi-stability condition depends on the geometry of the curve. Okay, so now algebra and computation. So my battery ran out in the train, so I did not have the slide animation. Please understand. So if you have a homogeneous ideal, then you take the minimal grade-free resolution, and Bj is you take the jth step of the resolution, and the maximum degree of the generators is Bj, the Betti number. Then I is called M regular if this inequality holds. So probably everyone knows the definition by now. And there's a small proposition in my paper with Brendan Hassett is that a bicanonically, so it's the case when you take nu equals to 2. Okay? And you take nu equals to 2, then and you do GIT, then a bicanonically embedded C semi-stable. I did not explain this stability condition, but there's another very geometric condition on the curve. You take these curves, then it is too regular. It's a small part of my paper. And the key point is that this is the regularity is completely defined in an algebraic fashion. Of course, you know that there is a cohomological formulation, but this is algebraic, and C semi-stability is completely geometry. So the geometry condition, from the geometry condition, you're going to get something algebraic. Now, so I think I'm going to show you the picture of C semi-stable curve. But look, it's not very important. I'm showing you two curves that are not C semi-stable. But the important point is that it's just a very geometric condition. And so from the previous proposition, which was that some sort of semi-stability implies a very small regularity, I came with this conjecture that you take a look at the Hilbert scheme. Then Hilbert scheme is going to be decomposed into locally closed subvarieties in which the regularity remains the same. Okay, and there is going to be the locus of maximal regularity. And the conjecture is that if an ideal is of maximal regularity, then it should be unstable. So here, algebraic condition and geometric condition, they are very intimately related in this fashion. There are counterexamples where unstable points have a fairly low regularity. But if it is of maximal regularity, then it should be GIT unstable. And here's another theorem that is of interest to algebraists and computational algebraic geometers. So an ideal has a semi-stable empty Hilbert point. So remember, we defined the Hilbert point by using this coefficient matrix in the Grassmannian. And it's GIT semi-stable if and only if for every integral weight factor summing to 0, and for every g, every linear coordinate, this is m plus 1 by the way, the degree m monomials not in the initial ideal have negative total weight. It's a mouthful, but it's a very simple condition to check. So what do? You take any monomial order, you compute the Grosvenor basis, then you get the initial ideal, and you get the monomials not in the initial ideal. Since you have this weight vector, you can easily compute the total weight. Okay. So if you can if you just compute that, and if it's negative, then it is semi-stable in that coordinate. Now you change the coordinates and do the same thing for every coordinate system, then you have checked the semi-stability condition. So this criterion, of course, can be checked effectively by computing the Grosvenor basis. And the point here is that the complexity of Grosvenor basis computation is, of course, very intimately related to the regularity. So the famous theorem by Bayer and Steelman is for the reverse lexicographic order, the regularity of ideal equals the regularity of the generic initial ideal, right? And for Borel fixed monomial ideals, the degree complexity, which is the maximal degree of Grosvenor basis computation reduced to Grosvenor basis, it's the same as the regularity for those monomial ideals, Borel fixed monomial ideals. Therefore, the corollary of this theorem is Grosvenor basis computation complexity equals the regularity. So computation and the algebra are related by this theorem. And I have a student, I'm sure that this is not his name. How do you spell your name?
L-O-H.
L-O-H, yeah. So it's not, in Korean it's no. But so he recently proved the converse to Bayer and Steelman. So if this is true for every ideal, then the monomial order must be reverse lexicographic. I think it's a fairly neat theorem. And here's a conjecture, interesting conjecture of Bayer and Steelman. If a homogeneous ideal has a GIT unstable Hilbert point, and I intentionally wrote it in a very faint green and gray because it's very vague. This is a very vague conjecture, admittedly, that there is a preferred coordinate system in which Grosvenor basis computation is the fastest. That conjecture was in a paper by those two authors in the 80s. And so there was a title and then one. And then there still is in the same title with number 2. Okay. So I recently met Dave Bayer and asked him about this conjecture, and he could not prove it because he did not know the statement. Right? If only he knew the statement, he could prove it. But right. So that's so. If you look at their paper in the Journal of Symbolic Computation, then they show some examples of Grosvenor basis computation. And what they show is that in some coordinates, Grosvenor basis computation was much more difficult. It involves very GB members in very high degree. And if you choose a coordinate carefully, then there's a really special coordinate system where GB computation is much faster. But then the negative thing in that example was that if you choose the coordinates generically, then it's the fastest. So what's the point of choosing this special coordinate system, right? So this is why the conjecture was not, they were not able to formulate the conjecture in a precise manner. And I think I can formulate it quite precisely now because of this theorem, recent theorem by myself and a student of mine, Park. Park is not too much of an information here, but he's one of my students. So any homogeneous ideal is Hilbert stable in generic coordinates. So look, if you look at this conjecture, the quantifier is that the ideal is GIT unstable in that coordinate. But if you look at this theorem, any ideal is going to be, if you choose coordinate system generically, it's going to be stable. That's why the examples are in this way. If you choose coordinates generically, then it's faster. And outside this generic set of coordinates, there are special coordinates. Okay. So this is just a more general statement of the previous theorem with my students. Not just the Hilbert point, but if you have reductive group acting on and a rational representation, then any point is stable with respect to a generic maximal torus. It's a pretty simple theorem, and any person experienced in GIT should believe it, but it's surprisingly there hasn't been any proof written. And now the mth state polytope of I, this formulation is due to Sturmfeld, is defined to be, you take an initial ideal and you just add all the exponent vectors as this proceeds run through all the monomial orders. Okay, I'm sorry, this is missing convex. You're taking the convex whole of those points, and the GIT says the empty Hilbert point is unstable if and only if the zero is not really zero, it's the barycenter, but some barycenter or the origin is not contained in the state polytope. Okay, so you see that this, as you see, state polytope is related to the initial ideal, Grosvenor basis computation, the convex and the volume, and it is also related to the GIT stability, the geometry, and Grosvenor basis computation and regularity. They are all connected in this manner. So there is a famous theorem due to Kempf, which was a conjecture of Mumford, that if something is unstable, then there is a coordinate system in which the origin or the barycenter is not in the state polytope. This was in the previous slide. And the distance to the origin is the closest. All right. So if you think about this statement, then to compute the state polytope, you have to compute the universal Grosvenor basis. The exponent vectors are exactly the exponents of the Grosvenor basis members, right? So it's related to the Grosvenor basis computation. Now, if it does not contain the barycenter, then the distance from the barycenter to the state polytope, it dictates the complexity of Grosvenor basis computation. Okay.
That's your conjecture.
Conjecturally, right?
And the term order you use is the direction from the polytope into the. It's like a
right,
facet.
right.
You pick a facet that separates the polytope from the origin. What term order you want to choose?
Well, what do you mean? What term? To compute the state
computation, you have
right.
to take a term order. So there's still a state polytope. There's still, many initial ideals. But you want to take one that is on a facet close to the origin, or?
Oh, the vertex closest to the origin, and it's going to be given by certain monomial order.
So that's the term order.
Right. Yeah, that's the term order that you want to.
You claim that that's the fastest.
Right. And there are, so I'm not really showing the full picture of my results about the state polytopes. The important thing is that if you change coordinates, then you're going to get different state polytopes. And as you can imagine, there are finitely many state polytopes that you can get. And there is a Zariski open dense subset of the general linear group where the state polytope remains the same. You take away that set, and there are boundary, and you can, in that boundary, so again, there is a Zariski dense open set where the state polytope remains the same. Okay. So if you think about that picture, and this, you combine it with this CHEM's worst one parameter subgroup, then you can come up with this statement conjecturally. I should not have put my name there, but it's okay. So among all coordinates with respect to which I is Hilbert unstable, so that was missing in, and you can precisely describe what these coordinates are. If the ideal is given, then you can compute. You can precisely state what this generic coordinate means in terms of the equations in the ideal. Therefore, you can you get rid of those generic coordinates, and away from the generic coordinates, there is a special coordinate system in which GV computation is the fastest. So I'm going to finish my lecture with this simple slide. Thank you very much.
Thank you very much.